Ever wondered how AI agents actually work? In this video, we will go through the orchestration process with a super AI solution architect assistant. First, I'll show you the architecture of the entire project, and then I will walk you through the code and how orchestration works with agents. Let's get started. So you have a user that is asking a question to your solution architect assistant, and we're basically giving our LLM hands, so the capability of performing actions. So we will define agents, and agents are defined with action groups. Action groups have Lambda functions that you can point it to, and an API schema. So in the API schema, you will define basically like all of the APIs that your LLM is able to use along with a description. And you need to be very descriptive in those descriptions in plain English, because the LLM will read through the description to try to understand what each of those functions is actually doing. For example, if you ask a question about the architecture of your company, and you have this first function called answer query that is connected to a RAG, so retrieval augmented generation, to get information from your company, then you can ask the question and the LLM will think to itself, if I need to answer a question about my company, I need to use this first tool. So it will go through a Lambda handler, and the Lambda handler will trigger the answer query function, get the information from your RAG, and then send the answer to your user. If the user is asking a question, for example, something like, can you generate the Terraform code for this architecture, and you have a function that does this, and it says in the description, then your LLM will be able to find that function with the API root, YakGen, and trigger the function that will drop the Terraform file inside of an S3 bucket. And if you ask it a question about the estimation of a cost of an architecture, then you put this in the description, and the LLM will be able to know that it needs to use that function to estimate the cost of an infrastructure. And we'll see in detail how it works in the code. So let's dive into the code now. So here we are in the Amazon Bedrock console, and we have access to our agents. And so we have deployed it, and when you create your agent, you create action groups. And each action group is defined by a Lambda function and an OpenAPI API schema. We'll see later what it is like. So if you open the OpenAPI schema here, you can see that we have the different API calls and the descriptions. So here, for example, I have the answer query function where I just want to have general knowledge about the architecture of my company. I created a RAG where I can retrieve information from my company, and I put this in the description. Like the answer query function allows to answer specific questions about my company's Swissbox app by querying a knowledge base and everything. Like you can be very descriptive. Also, the second API root is called YakGen, and basically it's a function that allows your LLM to generate a Terraform file depending on whatever architecture you're trying to build. So you see in the description it says this function allows to generate the Terraform code based on the requirements specified by the customer, etc. And we have a third API root called Yak Estimate tool, and this function allows us to call a certain library called InfraCost and estimate the cost of an infrastructure from a Terraform file. So here are all of the calls for the APIs, and here we have the Lambda function. And our Lambda function actually lives inside of an ECR container, and here is the image of the container. So this is how it looks like in my code. We have a Docker file, and here we install everything we need to run those Lambda functions. So we install the InfraCost, and we also have like the index.py where we have the description of the API path that I'll show you. So here is basically the handler. This is where the Lambda function handler handles all of the API requests and route them to the appropriate tool function. If we scroll down a little bit, we can see the process API request, and this is where we have our API handlers. And this is where the LM knows, actually the Lambda function knows which function it needs to run. And here we have all of our functions. You can define the knowledge base ID of your knowledge base, and also the region and the path to your S3 bucket. So for example, here for the function answer query tool, this is where we can retrieve data from our knowledge base. So just define the ID a little bit above and you'll be fine. And here we ask the question directly to the LLM. We also have the YakGen tool where we can generate Terraform file from a request. So here we have a pre-prompt, and then we send this with the query of the user to Claude 3.5 Sonnet. And from here, we have the path to the S3 bucket where we are going to drop the Terraform file, and we have the line to upload the file to the S3 bucket. And finally, we have this third function, the Yak estimate tool, where we can estimate the cost of an infrastructure based on the Terraform file. So the first step that we are going to do here is to get the latest Terraform file from S3. And from here, we download the latest file locally. And then we run infracost. And infracost takes the Terraform file as an input and outputs a text where we have the breakdown of the cost of the infrastructure monthly. From here, we created a pre-prompt where we send this along with the text of the report of the infracost. And we send all of this as a context to Claude 3.5 Sonnet. And it is able to actually make a summary of the entire output of infracost and estimate the cost of our infrastructure. So this is in the entire project. So now we're going to test our agent. I prepared a fairly complex query where I'm saying basically I would like to add powerful analytics with data warehouse to the SwissBox app. The solution must be fit for near real-time insights of application logs. It needs to be plugged to a dashboard for data visualization, make it the most cost-effective possible, generate the Terraform file for it, and estimate the cost. That's a very long query, but we'll see how our LLM is able to reason and think through it. Here I'm launching the query, and we can see the trace. So the trace is basically the chain of thought, so the reasoning. As you can see here, the LLM is actually thinking to itself. This is not the output that it is giving to the user. It's actually something that it's telling itself. And it's basically saying, in regards to what I sent as a query, to add powerful analytics with a data warehouse to the SwissBox apps that can provide near real-time insights from application logs and connect to a dashboard for data visualization, I will need to first understand the existing SwissBox architecture and data sources. Second, design a data pipeline to ingest and process the application logs. 3, set up a data warehouse solution for analytics. 4, configure a dashboard for data visualization. 5, generate the Terraform code to provision the required AWS services. 6, estimate the cost of the proposed solution. And to get started, I will query the knowledge base to understand the SwissBox architecture. So this is pretty amazing because it made a plan, basically, of the different steps that it needs to go through in order to answer the question. So here we see that now it has decided that it needs more information about my infrastructure, my company. So it's querying the knowledge base. And here you can see that it has gathered some chunks from the knowledge base where it's actually retrieving relevant information about what it's supposed to do. Step 3 of the chain of thought here, we see that it's actually making comments about the bits of information that it retrieved from the knowledge base. It says the knowledge base provides helpful information about the existing Swissbox architecture and data structure. It is a serverless application built with services like S3, Lambda. It goes on with a lot of details. Like to add analytics capabilities, we can set up an analytics pipeline to ingest and process the application logs from services like Lambda and API Gateway. So you have the entire thinking process of this solution architect AI agent. And funny enough, now it goes through, like it still knows that it needs to figure out the Terraform file. So now that it is, like the sentence before says, next I will generate the Terraform code for provisioning this analytics solution and estimate the associated costs. And once it has said that, it goes through the description of the API schema that I showed you earlier and knows that the right API path to do this task is the YAC-gen, and it will execute a Lambda function for this. It's thinking to itself also, generate the Terraform code to set up a serverless data analytics pipeline and so on. Here we see that it has done all of those steps, generated the Terraform file, and it has dropped it to the S3 bucket because this is how we have defined our function earlier in the code. So this is where we can find our Terraform file. If you see in step 4, the LLM is actually aware of the fact that the Terraform file has been dropped to the S3 bucket. And it's saying, so the YAC-gen tool has generated the Terraform code for provisioning the serverless data analytics pipeline and saved it to an S3 bucket. Next, I will invoke the YAC estimate tool to get a cost estimate for this solution. And from here, it knows that it needs to use the third tool. So by itself, it has used different functions in the OpenAPI schema that we gave it. Now, to estimate the cost of the Terraform file, it is retrieving the Terraform file inside of the S3 bucket. You can compare the two names of the files and you can see that it remembers from the step before where it had dropped the Terraform file for this architecture specifically. And now we have it. It's able to read the text of the cost and make a breakdown of the monthly cost for each of the services. And now it's actually aware of the fact that it has provided a detailed cost breakdown for the proposed serverless data analytics solution. It's even stating like the total estimated monthly cost is around $50. It's funny, it's even commenting, which seems reasonable for a small to medium-sized application like Swissbox. I now have all the necessary information to provide a final recommendation to the user. It's not even the output yet. The output is that last bit, where it's like compiling everything together with all of the different services, and it's actually also giving insights of why it has thought of certain services and why it thinks it is cost effective. So we've seen that the total monthly cost estimated is $50. What if now we ask it to make it more scalable? Let's see what kind of reasoning it will go through. Now we can see that the first thing it's thinking to itself is, to make the proposed analytics solution more scalable, we can take advantage of some of the auto-scaling and serverless capabilities of the AWS services involved. And again, it goes through the different steps of what it needs to do in order to answer the question. It's also saying we will need to regenerate the Terraform code and get a new cost estimate. So I did not even ask for it, but it's aware of our conversation and my concerns and everything. So it's not only giving me a solution that is more scalable, it's also aware that it needs to give me the Terraform file and the cost estimation for this. So again, It goes through the OpenAPI schema, understands which functions it needs to use, drops the Terraform file inside of the S3 bucket. Step 2 goes through the OpenAPI schema again and makes the estimation cost for the last file that it has dropped there. And this is pretty impressive. Actually, it knows that the cost is higher now because it's commenting, as you can see at the end of the reasoning. So it's pretty impressive because it knows that the more scalable solution is more expensive. It's saying the updated cost estimate shows that the more scalable analytics solution using Redshift as a data warehouse will cost around $297 per month, and that this is higher than the previous Athena-based solution due to additional costs of the Redshift cluster and Kinesis data stream. And see, like the last sentence also says, to provide a complete recommendation, I will check if the original Athena-based solution can meet the scalability needs by querying the knowledge base. And so it wants more information. It just wants to make sure that the architecture proposed is a good one. So it goes back to the knowledge base and actually checks for more information. And at the end of its search, it's saying the knowledge base search results indicate that Amazon Athena can provide good scalability for application log analytics use cases, being a serverless service and everything. So now it's even trying to help you more to understand the thinking process of what it went through. And so like the last sentence, given the lower cost and serverless nature of Athena, I will recommend the original solution for now, while highlighting the potential to scale up to Redshift in the future if needed. So I think that's really impressive. I feel like I'm actually talking to a very knowledgeable solution architect. It's even sending you, like here, we're still in the chain of thought, but it's compiling everything to give it to you in the output. So to summarize, we just saw how to give our AI the possibility to use functions. For this, we created action groups where we defined an OpenAPI schema and Lambda functions to handle API routes. By giving a description to each of the functions on the OpenAPI schema, we allow the LLM to understand what the function does. Thanks to its chain of thought, the LLM is able to decide itself if it needs to use them or not. If you want to learn more about the code, check out our GitHub repo in the description. And if you enjoyed this video and want more hands-on technical content, be sure to like this video and subscribe to the AWS Developer YouTube channel. Happy coding!